Hello and welcome to the third lecture in the course Mathematics 2. Today we're going to look at some properties of gradient vectors. So in the first part of the course, we will look at why the gradient vector is orthogonal to level curves of a function of two variables. So first recall what the gradient vector is. So if we have a function of two variables, like example, if our function is f of xy is let's say x cubed minus xy, right? So then the gradient vector is just the vector of two partial derivatives. So the first is partial derivative of the function with respect to x. So it's 3x squared minus y, and the second entry is the partial derivative with respect to y, which is just negative x. Right, so and then we can compute the gradient vector for any particular value of x and y. So for example, nebula f evaluated at the point say 2, 1 is going to be is what a 3 is 3 times 2 squared minus 1 and minus 2. So which is 3 times 2 squared is 12, minus 1 is 12 minus 1 is 11, negative 2. Okay, so this is the an example of a gradient vector. Okay, now in this section we are going to discuss this property that the gradient vector is always perpendicular to the corresponding level curve, or in the next section it's going to be a level surface instead. So let me explain what it means first. So let me show you, well, use this example, right? So let me hide everything here. Right, so I'm going to use the same function. So f of xy is x cubed minus xy. Right? Now, so what you see here is the level curve of this function corresponding to the value 6. Right? So x cubed minus xy equals 6. Right? So at the same time, we see that the point 2.221 is on this level curve. Right? So because its coordinates satisfy the equation of the curve. 2 cubed is 8 minus 2 times 1 is 6. Okay, correct. So this point P is on the level curve. Now, if we draw the vector with coordinates, so as I just computed, right, so let me check again. So as I just computed, so the gradient of the given function at the given point is 11 minus 2, right? So if it means that if we start at the point 2, 1 and draw this vector with coordinates 11, so this is going to be 11 and this is going to be negative 2, then this resultant vector is going to be perpendicular to the level curve, and this is what it looks like, right? So okay, so to get 11, 2, 2, 1, 11, 2 plus 11 is 13, right? And 1 minus 2 is negative 1. So this is what this gradient vector looks like, right? So if you plot it as a vector, so then what you see is just that it is perpendicular to the level curve. That's basically this how you see this property. Okay, I'm sorry. So let me switch back to my slides. Now, this is actually a proposition. Well, proposition is another name for a theorem or a lemma. I'm not sure why. Well, I didn't make the slides myself. So as I said, these slides were mostly developed by Dr. Tangyok Chu, but now I'm taking over. She has retired. So the word proposition here, it's like a mathematical statement, right? So it's something about mathematics. So it's essentially the same thing as a theorem or a lemma or just a statement. right? Now, this proposition tells us that basically if we have a function of two variables and we draw a level curve of that function, and then if at every point of that level curve we compute the gradient vector, then the gradient vector is going to be perpendicular or orthogonal, which is the same thing, to the level curve. So here is a picture. So this is what it looks like, and basically I just showed you a similar example that I plotted myself in Desmos calculator. You can also try to experiment with it in Desmos calculator. You will have to figure out how to plot vectors in Desmos calculator, but there are some kind of guides on the internet that can help you. So it is true, right? So now I'm going to do something that I will seldom do in this course. I'm going to prove this, right? So now mathematicians always prove all the mathematical statements, all propositions, theorems, lemmas, and so on and so forth. Now, when we teach non-mathematicians, we very often we don't really bother proving it because you guys don't really need a lot of proofs. But sometimes it is good to insert a little proof because it helps understanding. Okay, so but if you don't really understand it, don't worry too much because uh, in the end of the course, proofs are not going to be tested, right? So what I am going to do, I'm going to explain how we can prove a mathematical statement, right? So, if we have a two variable function here and a level curve, right? So what I'm going to do now, I'm going to differentiate this with respect to an x, to x. Okay, so how do I differentiate this with respect to x? I'm going to differentiate this with respect to x. Using the chain rule, right? So to differentiate the left-hand side, I will write df dx times dx plus df dy times dy dx. And the right-hand side is a constant, so its derivative is going to be 0. Okay, now the dx over dx is just 1, right? So because we are differentiating a variable with respect to the same variable, right? So and the resulting thing is I'm going to just use fx instead of df dx. So the resulting thing is going to be fx plus df dy is fy times, well, dy dx. So notice that if you really think of this a level curve um, as a curve in the plane, then a little part of this curve near the given point. So here you can think of this as y, well, as an implicit function. So y is a function of x, right? And if y is a function of x, then there is just one dependent variable and one independent variable. So I should really use just the usual notation. Instead of the partial derivatives, I'm going to just use the usual derivatives. Okay, so here is the equation that I've just derived. And notice that this equation, you can write it like this: fx times 1 plus fy times dy dx is 0. In other words, it tells us that the vector fx, fy, the dot product of this vector with the vector whose first entry is 1 and the second entry is dy dx is 0. Right? So in other words, it tells us that the gradient vector is perpendicular to this vector whose first entry is 1 and whose second entry is the derivative of y with respect to x when we consider y as an implicit function of x. All right. Now, the remaining thing is to explain why this vector 1 comma dy dx is parallel to the tangent line of the level curve to the level curve, right? So to do this, I'm going to do the following thing. So I'm going to, again, so think of y as an implicit function of x, right? And when you think of y as an implicit function of x, recall that the geometric meaning of the derivative, right? So if you have like coordinate axis, and then this is your function y as a function of x, and then you take any point, right? So then you take the tangent line, take the horizontal direction, take this angle between the tangent line and the horizontal direction. So the slope or the tangent tan alpha of this angle is actually dy dx, right? So at the same time, how can you evaluate the slope? So you can do the following thing. So you can take, I don't know, take the unit distance to the right, if this is like the length 1, and take the vertical distance. So then this vertical distance is going to be dy dx. So why is this so? Because the tangent of any angle is the opposite side divided um, by this side, right? So when we write the tangent angle is dy dx, so it's the same as writing the dy dx divided by 1. So which is why it really works. Okay, so right, so this is what it means. At the same time, so we can rewrite this tangent, the equation of this tangent line um, as as what as y equals, well, this dy dx basically times x minus the given point x0 plus y0, right? Yeah, okay. um, and this dy dx coefficient here in front of x precisely means that this is the slope of the tangent line, right? So okay, now what we see here from this picture and from this equation is that this vector, whose entries are 1 and dy dx, is in fact parallel to the tangent line of the level curve, right? So which essentially is it means that we've just proved the proposition, because the equation that we wanted to derive tells us that the gradient vector is perpendicular to this vector, and this vector is in fact parallel to the tangent line to the level curve. So which means that our gradient vector is in fact perpendicular to the tangent line to the level curve, which is precisely what we wanted to prove. All right. So now here is an example how we can use this kind of machinery to derive, well, to solve some exercise. Okay. So here we are supposed to sketch the level curve of the function f, which passes through the given point. Right. So my x is 1 and my y is -1. So generally speaking, a level curve looks like this. So it's f of x y equals k. So the question is what k is in this situation. And so we know that x times x minus 3 minus y equals k. At the same time, we know that x is 1 and y is -1. Right? So this is like 1 times 1 minus 3 minus -1. 1 minus 3 is -2, so this is -2 plus 1, so this is -1. Okay, so my k is -1. Right? So it means that my level curve is the given function equals -1. Okay, so let me rewrite it. Maybe I'm going to move y to the right hand side and -1 to the left hand side. So x times x minus 3 plus 1 equals y, or y equals x times x minus 3 plus 1, or I can, to differentiate it, it's probably easier if I rewrite it as x squared minus 3x plus 1. right? So this is my f, and now the question is to sketch the level curve. So the first thing to do is to sketch the level curve, right? So let me sketch the level curve. Now, this form is this is a quadratic function, so it's the graph is called a parabola. So basically, the first choice when you plot a parabola is whether it is concave upward or downward. So this you can see from the coefficient at x squared. So the coefficient at x squared is positive, so which means that it's this case and not this case. Right? Okay, so we know that it is a parabola concave upwards. Cool. Now, um, what is the apex of the parabola? How do we know? So basically, we have a very convenient form here, x times x minus 3. And if our quadratic function is expressed as x times x minus something, then the apex is precisely half of this, is 1.5. Okay, so the apex here is 1.5. And what is y corresponding to the apex? So we know that x is 1.5. So let us substitute y. So y is 1.5 times negative 1.5 plus 1, so which is minus 2.25, I think. Yeah, plus 1, so which is minus 1.2 to, sorry, 21.25. Okay, so I know that the coordinates of the apex of my parabola are 1.5 and negative 1.25. Okay, cool. What remains to plot is to probably, let me sketch the coordinate axis. So 1, 2, 3, 1, 1, 2. Okay. So let me use a different color. So the apex of the parabola is somewhere here. So what is um, the y-intercept? So what if x is 0? So if x is 0, then my y is 1. Right? So it means that this point is on the parabola. So if x is 1, then my y is, well, I think I've just computed it, is negative 1, right? So this point is also on the parabola. Well, and by symmetry, and again, so it is easy to compute that the point 2, 1, 2, negative 1 is on the parabola, and the point 3, 1 is on the parabola, right? So my parabola basically passes through all these points. So here is the sketch, and the remaining thing is to find, to plot the gradient vector, right? So the gradient vector at the point negative 1, negative 1. So it is this point. Let me change the color again. Now, the gradient vector is perpendicular, so it should be kind of on this line. But whether it, so in which direction it points and what is its magnitude, we need to figure out. So let's compute the gradient vector. So um, nebula f is, first I differentiate with respect to x, and this is going to be 2x minus 3. Now I differentiate with respect to y, and the derivative with respect to y is negative 1. Yeah, maybe I should write it again, so that my f of x, y is actually 3. Sorry, x minus 3 minus y. Okay, and it should be equal to negative 1. Right? So the level curve is negative 1. Okay, so nebula f is 2x minus 3 and negative 1. At the given point, nebula f at the point negative 1, is, sorry, sorry, not at -1. So my p um, is 1. So nabla f at 1, -1 is going to be -1, -1. So as calculated here. All right. So I should draw the vector with coordinates -1, -1, starting at the point 1, -1. So this is what it looks like. So this vector. Okay. And okay, so this is what it looks like. And again, probably I should insert this vector. Okay, so that's the end um, of this example, and that's the end of this part of the lecture.